Law of change of kinetic energy. We can start from second Newton's law, so-called law of force. The mathematical formulation of this law is here. So F is equal derivative of, can you see what is it? It is momentum, derivative of momentum with respect of time. So this is mathematical formulation of second Newton's law. When we multiply this law by element of dr, what is dr? We know it. When we consider, we observe the position of some particle in three-dimensional coordinate system x, y, z. So r is a displacement vector. So r is a displacement vector, and dr is a element, infinitesimal element. So it's an element of displacement vector. So if we multiply this equation by elementary part of displacement vector, we can rewrite this equation like this. So, and we can swap denominators, so we can put dr to numerator and repeat this denominator and this differential put here. So this is velocity again, so we can rewrite it to new form, so it is v by d mv. We can continue, so we can put out m of the brackets because m is a constant, so it is m by v dv. And now we will concentrate to this term. So let's continue in this way. If we have v by v and we make a differential of this, so it is, so we can, it's a differential of multiplication, so we differentiate the first term and we can rewrite second term, plus we rewrite first term and we differentiate second term. So it is 2v dv. So we can say that 1/2 of d v by v is equal v dv. And this is what we have here. So we can say that 1/2 of d v square is v dv. Why v square? No, because there is a scalar multiplication. Okay, it's a scalar multiplication of vectors. I hope you know it. If you multiply one vector in scalar multiplication by another vector, okay, and they are the same vectors, you get square of the size of the vector. So we can continue here. So we can write that it is in fact m by 1/2 of dv square. So we can come to the beginning and we can say that f dr is equal a half of m dv square, and we can call this elementary work of force. Okay, so dv is elementary work of force. Yes, so it's very important. So dv is elementary work of force and is equal to scalar multiplication of force and elementary displacement vector. So what about we integrate this equation? So we get integral of f dr from state 1 to state 2 is equal integral of this from velocity 1 to velocity 2. So we get a half of m v2 square minus a half of m v1 square. Okay, so this is work of force, and this is kinetic energy at state 2, and this is kinetic energy at state 1. So kinetic energy at state 2, this is kinetic energy at state 1. And generally K, 1/2 of mv square, is a kinetic energy of particle. So we can say that work of force, what is a resulting force, acting on particle m on trajectory s, is equal to difference of kinetic energy at the end of the process and at kinetic energy at the beginning of the process. So work of force is equal to difference of kinetic energy at the end of the process and at the beginning of the process. If we calculate this work, we can use this calculation in this form, where usually force is given as a vector by its components, and when we know that r as a displacement vector has components x, y, z, so differential of this vector has components dx, dy, and dz, and these two vectors we need to substitute here. So how we practically multiply these two vectors? So f dr is f vector by dr vector, and we multiply it in scalar form, so we multiply corresponding components, x component of f by x component of displacement vector, differential, and y with y, z with z, and we add them together.